So now let's move towards step 2 for defining the Ito integral. So I will present in the step 2 I will present a lemma that is called an approximation lemma. We will not get into the proof. Let me reiterate. If you want to know the proof of this approximation lemma, then you can comment below and we can discuss online. That's not going to be free session for sure. So we have this nice approximation lemma that says that if you have suppose you have f from L to AD of A to B times omega. By the way, this space is called space of adapted stochastic processes. So suppose you have a function from L to AD of AB times omega, then there exists a sequence Fn of t of step adapted stochastic processes, let's say stochastic processes such that, so of course this sequence is also coming from this same space. So the same space. So we, for given any f, we can find a sequence of step processes from the same space such that we have following limit, such that we have limit n goes to infinity of A to B, expectation of Fn of t minus f of t dt 0 as expected. So that means you can say that for given any f from this space of adapted stochastic processes, we can find a sequence of step functions that is converging to this this stochastic process. And of course square here, there is a square here, because this is roughly speaking, this is norm of this space. So as we have already discussed, so this is norm. So norm on this space for any f, we can define norm on this space L to AD square of this is A to B expectation of f of t square dt. So this convergence must be in this norm, right? In other words, simply I can put the following approximation lemma in this words, that if you have any f from this space L to AD then this function can be approximated by another sequence of step functions from this same space. So for every given process you can find a step function sequence from the same space that is converging to this function. Or give me a function from this space, I'll give you a sequence of step functions from the same space such that my sequence will converge to your given function. So you are giving me some function here in this space, whatever this space is, I'll give you a sequence in the same space that will converge to your given function. Next that we are going to do is we are going to define the integral, Ito integral for the function given any function. So what will I do? You will give me any function f of t and you want to know what is Ito integral of this. So what is Ito integral of this? F of t w d dt. What is this? So what will I do? For given function I will find a sequence. of step functions, and I will compute Ito integral for this sequence because I know already what is how to compute the Ito integral for the step functions. So I will compute this Ito integral for the sequence of these step functions, and what will I do? I'll take the limit of these integrals of the step functions. So that will be basically the integral. This limit will be equal to this quantity. So in other words, whatever the limit is, I will give it the name, or I will define the integral of this function that you want to integrate stochastically, or you want to know what is the stochastic integral of this. So it is going to be equal to this limit. Okay, I hope that makes sense. So in the third step we are going to do that. Okay, so let's define it precisely. Definition: let f of t comma w be from L to AD of AB times omega. Suppose fn of t comma omega be from L to AD of this be a sequence of step functions such that this fn of t comma omega converge to this f of t comma omega in this sense. So it is converging to this. Then this sequence IFN defined by A to B Fn t omega dBt converges in L2 of omega, and okay, so and we call this limit, which limit? This limit. So the limit of this sequence n goes to infinity of I of Fn. We call this limit the Ito integral, of f of t comma omega that we had picked in the start. In other words, this function. So you want to define the Ito integral of this function, you will pick a sequence of step functions, and then you can show that of course step functions which are converging to this. Then you can show that the sequence of Ito integral of these step functions is also convergent, and the limit of that sequence of these integrals of the sequence, or the Ito integral of the sequence is called the Ito integral of the function this. So let's define it in a very easy way. So you pick a function from this L2 AD. So you have a function from this space. For this function you can find a sequence from the same space such that this sequence is convergent by approximation lemma to this function that we want to define Ito integral for. So we want to define Ito integral for this, so we will pick a sequence of step functions that is converging to this, and then we can show that the sequence of Ito integrals for this sequence. So this sequence is basically the Ito integral of this step function sequence. We can show that this is convergent in L2. So based on this, because this is convergent, so we will say that the limit of this sequence is basically the integral, Ito integral of this. So in other words, we can finally say that this A to B f of tw dbt is nothing but limit n goes to infinity of this sequence A to B, the Ito integral of the step functions. Thank you.